Okay, sir. I think that started recording.
Excellent. So we can start now. Wunderbar.
By the way, I don't know if Evan is already back. Evan?
So, hello.
Oh, he went to the video room, so.
Hello?
Yes.
Yeah, it's recording now. I already asked
Excellent.
them.
Thank you. Thank you very much. Okay. So let's then start our lecture finally. So I wanted to say something. I told you so you know this play of by Shakespeare, Hamlet, where the guy says to be or not to be, and then as a question and then gives an answer. Well, so let me ask the question, a similar question. BEC or not BEC, where BEC stands for Bose-Einstein condensation. So how do you decide whether you do have or you don't have Bose-Einstein condensation? Well, let me remind you. The criterion to figure out whether you do have or you don't have Bose-Einstein condensation is you have a certain number of particles. You try to saturate this number of particles by filling up excited states. And therefore, you try to figure out whether this equation has a solution mu function of n with mu negative or equal to 0. If it has such a solution, then for a given, at a given t. If it has such a solution, then you say, well, the system is essentially filling up, saturating the total number of particles in excited states, and I have a nice negative chemical potential. There is nothing to worry about. By the way, this here is the density of states. Now, in certain cases, there is a critical temperature, T equal to Tc, for which mu at Tc is equal to 0. How do you find this critical temperature? You just try to solve the following equation. Integral d epsilon, g of epsilon, e to the beta epsilon minus 1 equal to n. Now, solving this equation, you will find what is Tc. Now, if the integral here is a convergent integral, then you will find a finite temperature, and therefore you say, well, the system has Bose-Einstein condensation. If for some reason, because the density of states is peculiar or whatever, you find on the right-hand side an integral that is divergent, then you will say, okay, my critical temperature is equal to 0. There is no Bose-Einstein condensation whatsoever. And the system is never displaying Bose-Einstein condensation. In the cases in which there is Bose-Einstein condensation, then you say, what is the condensate? The condensate is all the particles that are sitting in the ground state. How many particles are sitting in the ground state? Well, for temperature smaller than Tc, the number of particles in the condensate, is equal to the total number of particles minus integral d epsilon g of epsilon divided by e to the beta epsilon minus 1. Okay? So this is the total number of particles that sit in the condensate, while this integral here for temperature smaller than Tc tells you how many particles are outside the condensate. Okay? So all of this is clear, right? All right. So now, suppose that I give you a general problem. How do you then try to sort out this problem? Well, first of all, the basic equation is n equal to sum over p. In the discrete version is n equal to sum over p or sum over the quantum numbers of your system. Let's call them, I don't know, n for generality, m, 1 over e to the beta epsilon m minus mu minus 1. Now, in general, you can rewrite this as integral over d epsilon g of epsilon divided by e to the beta epsilon minus mu minus 1, provided you introduce a function g of epsilon, which is equal to the sum over m. M are the quantum numbers, generic quantum numbers of your system, sum over m of delta epsilon minus epsilon m. Right? You see that if I substitute this in there, I get essentially this discrete integral. So this is what should stay here in general. Okay, so therefore, whenever I'm asking you a question, suppose, of the type, I have a certain system with a certain spectrum in a certain dimensionality. Is there or isn't there Bose-Einstein condensation? Well, the simplest way you can use to answer this question, since essentially you have to figure out whether the integral here is convergent when you set mu equals 0, is to compute the density of states from this formula. So one is compute g of epsilon, and 2 is figure out the convergence of the integral d epsilon g of epsilon over e to the beta epsilon minus 1. Okay? So this is what you have to do in practice in order to figure out whether there is or there isn't Bose-Einstein condensation for a certain system. Why? Because if this integral is divergent, then the critical temperature is going to be equal to 0 necessarily. Well, if this integral is convergent, then you will have a finite critical temperature. You just have to solve the algebraic equation, corresponding algebraic equation. And there's no problem about it. So let me make an example of this procedure. Let us ask ourselves the following question. We know from what we have done yesterday that there is no Bose-Einstein condensation in two dimensions for a free system, right? So let me now consider the following system. Let me consider a system that is trapped in an harmonic trap, which is, by the way, the system in which Bose-Einstein condensation was indeed observed experimentally. So what does it mean to be in an harmonic trap? For example, let us focus on two dimensions, 2 equal to D, and let us consider a system that is sitting in a potential that looks like this. So it is a certain harmonic potential in one direction. No, not good. Certain harmonic potential in one direction and a certain harmonic potential in the other direction, right? It's sitting in a two-dimensional harmonic trap. I don't know how to better draw it than this. V, this is X, this is Y, whatever. So this is my harmonic potential. Now, if the potential is V of X and Y equal to 1/2 m omega 1 squared X squared plus omega 2 squared Y squared, what is going to be the spectrum, epsilon? What are going to be the energy levels of this potential? It's a question to you about quantum mechanics.
It's H omega 1 plus omega 2 n plus half.
No, I'm sorry, it's not.
It's H bar omega n1 plus 1/2 plus H bar omega 2 n2 plus 1/2.
Exactly. So the spectrum needs, in order to specify an energy level, you need two quantum numbers, n1, the principal quantum number for the harmonic oscillator essentially in the x direction, and the n2, the principal quantum number for the harmonic oscillator in the y direction. And the spectrum is h bar omega, h bar, I set it equal to 1. So omega 1, n1 plus 1/2 plus omega 2, n2 plus 1/2. Why it is so? Essentially because the problem is separable. I have two directions which are independent. So if you think for a second, the Hamiltonian is P1, Px squared over 2m plus 1/2 m omega 1 squared x squared plus the same thing for y. Right? And therefore, what you can do is you can write your wave function psi of x and y as psi n1 of x, which are, the harmonic oscillator wave function for x, times psi n2 y. Okay, so that's why you have this spectrum. Clear to everybody? Yes?
Yes.
Okay. So now this is my spectrum. Let me forget from now on about the 0-point energy. So this is omega 1 and 1 plus omega 2 and 2 plus, well, the 0-point energy, 0-point energy that I forget about from now on. It's just a reference point. And now I have to sort out whether a system of particles in this harmonic trap will display or will not display Bose-Einstein condensation. How do I sort it out? Well, I just have to solve the equation n equal to sum over n1 and n2. So this is the discretized version. 1 over
Sorry,
e.
Professor.
Yes.
What did you cross just now after n?
0-point energy is the 0-point energy, ZPE, 0-point energy.
I see.
Omega 1 over 2 plus omega 2 over 2 minus 1. So this is the equation I have to solve. I have to find a beta or a t such that this equation is satisfied. And I can rewrite this equation as follows, as the integral between 0 and plus infinity, the epsilon g of epsilon divided by e to the beta epsilon minus 1, right? Where g of epsilon is now equal to the sum over the two principal quantum numbers, delta of epsilon minus omega 1 and 1 minus omega 2 and 2. Okay? So this is the equation I have to solve. So let me first compute the density of states, right? So let me focus on the calculation of the density of states.
Professor,
Yes.
I have a question regarding solving the critical temperature.
Yes.
I mean, you also begin with this integral, right? I mean, in which case you actually use the momentum form, and in which case you use the energy form. Like, I mean, in previous derivations,
Well, that's what I tried to express here. So in general, you always start from a discretized version, right? So you will have some quantum numbers that could be the quantized momenta of your system, so 2 pi n over L, or could be the principal quantum numbers if you have a trap, or if you have some other potential are going to be some other quantum numbers. So in general, you will have something of this type, right? Then I'm saying you can always rewrite this sum as an integral over energies, provided the E is multiplied by the function g of epsilon. The epsilon is multiplied by the function g of epsilon, that is the density of states. Okay? So whether I have momentum sitting there or principal quantum numbers of an harmonic oscillator or whatever you want, you can always rewrite things in this energy form, as long as you calculate, provided you calculate your density of states. Okay? Is it clear?
Yes. How do you usually calculate the density of states?
Well, let's see. So let me Now, for example, I have to do it here, right? For this g of epsilon that is sitting here. So I have to compute g of epsilon equal to sum over n1 and then 2 or delta of epsilon minus omega 1 and 1 minus omega 2 and 2. Now, this can be seen as the derivative with respect to epsilon of the sum over n1 and then 2 of theta of epsilon minus omega 1 and 1 minus omega 2 and 2. Theta is the step function. You know that the derivative of a step function is a delta function, right?
Yes.
Okay. So I know I can call this object here the derivative with respect to epsilon of g of epsilon, big G. What is g of epsilon? Let's think about the physical meaning of this. This is the number of levels in my system with energy smaller than epsilon. Okay? This is what it is. Now, even though this is discrete, if epsilon is much larger than omega 1 and omega 2, then you can estimate the g of epsilon by
Sorry, what have you written in a red pen?
number of levels with energy smaller than epsilon.
Okay.
So I should have given you a lecture about deciphering my calligraphy. It could have been much easier for all of us. Anyway, so g of epsilon is written up here. So it's sum over n1 and n2 of theta epsilon minus omega 1 and 1 minus omega 2 and 2. And now I can estimate the sum if epsilon is much, much larger than omega 1 and omega 2. I can roughly estimate it by taking n1 and n2 roughly as they were, instead of discrete variables, passing to the integral, right? So writing this as integral dn1
So
dn2. Yes?
can you repeat the condition to go to the integral?
Oh, the condition is just that epsilon is much larger than omega 1 and omega 2.
Okay.
So the number of levels is very, very large and the discreteness is not important. Theta of epsilon minus omega 1 and 1 minus omega 2 and 2. And then, so this is equal to 1 over omega 1 times omega 2 integral d epsilon 1 d epsilon 2 of theta epsilon minus epsilon 1 minus epsilon 2, where epsilon 1 and epsilon 2 are, of course, so epsilon I is omega I and I, where I is equal to 2, 1, or 2. Well, now computing this integral is really straightforward. What you do is the following. You write it as equal to 1 over omega 1 times omega 2. And then you have integral between 0 and epsilon, d epsilon 1, integral between 0 and epsilon minus epsilon 1, d epsilon 2. This is the, is what I've written up before. You see that if I integrate over epsilon 2, I have to be between 0 and epsilon minus epsilon 1 because of this theta function. And then, because epsilon 2 starts from 0. And then epsilon 1 can vary between 0 and epsilon. That's it. So now this is equal to 1 over omega 1, omega 2, integral between 0 and epsilon d epsilon 1 of epsilon minus epsilon 1. And then this is equal to just a second. Why? I wrote something stupid, I think.
Sorry,
Yes,
why there is no issue function here?
I cannot hear you.
Why there is no issue function here on the last integral?
Why there is nothing from?
No step function. Step.
Can you write your question in the chat? I cannot hear you. Why there's no step function? Well, because here I have an integral between 0 and plus infinity of d epsilon 1 and d epsilon 2 of the step function. Now, I can write this as the integral between 0 and plus infinity. Sorry. I can write, so you see that if I fix epsilon minus epsilon 1, if I fix this variable, then epsilon 2 can vary between 0 and epsilon minus epsilon 1. This is written up here. And second, epsilon minus epsilon 1 has to be positive. And therefore, epsilon 1 has to vary between 0 and epsilon. Right? So you agree with me?
No. Can you repeat again?
Yeah, so what I'm trying to say is that epsilon 2 is varying between 0 because it cannot be negative, epsilon 2. See, the integral starts from 0. And epsilon minus epsilon 1. This is what is written up here. Okay, because of this theta function. So epsilon 2 can vary between 0 and epsilon minus epsilon 1. Now epsilon minus epsilon 1 has to be positive, right? Otherwise, all I'm writing doesn't make any sense. And therefore, what I get is that this actually goes, epsilon 1 can vary between 0 and epsilon. Okay?
I think, sorry,
Yes?
I think she's asking why there is no step function in the last line, but it's
Well, because
equal to one.
because you know, for in all these intervals, the step function is equal to 1, so there is no need to write it.
Yes.
Okay, so it's here, but it's 1. So in all the intervals in which I'm integrating down here, it is equal to 1, and therefore I'm not writing it. Okay.
Okay, thank you.
Anyway, so if you now do this integral, you will get that this is epsilon squared over 2 omega 1 omega 2. And now if you take the derivative of this with respect to epsilon to compute the density of states, you will get that your g of epsilon, which is equal to d epsilon of big G of epsilon, is equal to epsilon divided by omega 1 times omega 2. So this is your density of states for two-dimensional system in an harmonic trap. So now let me plug in this into my expression, into my equation. E to the beta epsilon minus 1. Well, you see that this integral here is perfectly convergent because g of epsilon is linear in epsilon. There is no singularity whatsoever. It's not a constant, it's linear and cancels the linear behavior of the denominator for small epsilon. Therefore, the logarithmic singularity that we have seen in 2 dimensions last time is not present here, even though this is a 2-dimensional system. Why it's not present? Because the system is 2-dimensional, but is sitting in an harmonic trap. Therefore, if now I set beta epsilon equal to x, I will get that this is t squared over omega 1 times omega 2 integral between 0 and plus infinity d of epsilon x over e to the x minus 1. Again, this integral over dx, not d epsilon, is a convergent integral. And therefore, I get that this is actually t squared over omega 1 times omega 2 times pi squared over 6. So t, c, in this case, is equal to omega 1 times omega 2 times 6 over pi squared times n, and then you have to take a square root.
Excuse me.
Yes?
Can you go back to the previous page?
Mm-hmm.
Thank you.
All right. So,
Sorry, Professor.
yes.
I think to get the result of the integral, it's not it's not easy. Right? So do we have usually to
Which integral?
No, the
Which?
last one, pi square.
No, but these are integrals. Let me, if I, just a second. So in general, if you have an integral, I mean, you can check it on this, you know, tables of integrals. Now let me try to remember how it works. If you have x to the power alpha divided by e to the x minus 1, then this integral is equal to the zeta, Riemann zeta function at alpha plus 1 times the gamma function at alpha plus 1. So now here you have alpha equal to 1. So for alpha equal to 1, you should be getting zeta of 2, gamma of 2. Now, I don't remember what is zeta of 2, but let's see. Riemann zeta of 2 is pi squared over 6. So this is pi squared over 6 because it's the zeta function at zeta equal to 2, and then gamma of 2 is equal to 1. Right?
Yes, so we have to know
So
this
that's
zeta function.
You have two? Yeah, of course. I mean, in general, you know, if this was the final exam and you're given an integral of this type, then if you write to me zeta of 2 times gamma of 2 is good enough. I mean, you know, you're not supposed to know what is the value of the zeta function at its argument equal to 2, right? All right. Even though I remember, it's actually an interesting thing to compute the value of the zeta function at its argument equal to 2. It was an interesting exercise. I think it was sorted out by Euler. It's one of the first exercises that was sorted out by Euler. I don't remember exactly. I think I've done it many years ago, but I don't remember the details. Anyway, all right, so this is what you get. So the purpose of this exercise was to tell you, look, if you want to know, so if you have a two-dimensional system, it's not that for any two-dimensional system, there is no Bose-Einstein condensation. There is no Bose-Einstein condensation in 2 dimensions in free space. But if you don't have free space, if you're in a situation like this one, then you might have Bose-Einstein condensation, right? So as in an harmonic graph. And I've shown you that this happens. Now, since you are, I know that this story of Bose-Einstein condensation is always kind of problematic. And since you all want to seem to be interested in doing exercises, let me ask you the following question, okay? And let's see who gives me. So now you should have paper and pencil, all of you. So the question is the following. Suppose that you have a system that has a dispersion as a function of momentum, which is P, some constant, times p to the power alpha. Okay? And the system is in d dimensions. So my question is the following. What is the condition on alpha to see Bose-Einstein condensation? So let's try to solve this question together. So what should I do in order to answer this question?
Compute G of epsilon.
Get the derivative first.
Get the derivative of what?
Of epsilon to p.
Of epsilon? So I should compute the density of states. So we agree on this, right?
Yeah.
Yes.
Is the formula.
Yes. So how do I compute the density of states? G of epsilon equal to sum over p, and then delta of epsilon minus epsilon p. This is the definition of density of states. So this is then L to the D divided by 2 pi to the D integral dp of delta of epsilon minus epsilon of p. Now here I forgot to write that it's an absolute value. So now what do I do? What do I do now?
Change variables.
Change variables. And no, before I change variables, what do I do?
Write dp in d dimension.
Write dp in d dimensions. Okay, I can write it in many ways in d dimensions. I can write dp equal to product over I dpi from 1 to d. Is it good?
We can choose spherical coordinates.
We can choose spherical coordinates because epsilon of p is a function of the absolute value, right? So we choose spherical coordinates. This is equal to L to the d divided by 2 pi to the d. Then I'm going to have the solid angle in d dimensions that we calculated a long time ago, but I don't remember what is the value now. And then we have integral between 0 and plus infinity of dp, and then you have delta of epsilon minus cp to the alpha, right? So what do I do now? What do I do? Guys, I feel like Super Mario, right? I mean, you're playing a video game with me. I'm solving integrals, and you should tell me what to do. Okay? So it's a video game. It's Super Mario integrals. So what should Super Mario do now?
Sorry. Since it's spherical coordinates, then you have like p
That's
to
right.
the power
I have
of d.
p to the power of d minus 1.
D minus 1. Yeah.
Yes, correct. Super Mario made a mistake. So what should I do now?
Compute n.
Compute what? In order to compute this integral, what should I do?
Change of variables.
Change of variables. So which variable should I choose?
Epsilon.
X equal to
CP.
CP to the alpha. Okay. So this is my change of variables. And then dx is going to be equal to alpha C p to the alpha minus 1 dp. Okay. So I can actually write it as, let's do things carefully. dp equal to dx over alpha c p to the power alpha minus 1. And this is, so p is equal to x over c to the power 1 over alpha, right? So therefore, this is dx over alpha c x over c to the power alpha minus 1 over alpha. Correct?
Yes.
Everybody agrees with me?
Why is it X not epsilon?
Epsilon. Well, is it important which variable, I mean, how I call it?
I mean,
It's integrated, so who
you
cares?
want to convert P to X, and
Yeah,
what about the
so,
epsilon there?
no, the epsilon stays epsilon. So this guy is not integrated, so it stays epsilon. So I transform this integral into, so let me erase this, into L squared over 2 pi to the d, omega d, and then I have integral 0 and plus infinity dp divided by alpha c x over c to the power alpha minus 1 over alpha. And then I will have p to the d. So p was actually x over c to the power d minus 1 over alpha. And then times delta of epsilon minus x. Okay?
I'm sorry, is it LD or
Is it what?
L to the power D, not L2?
Is it n to the power d?
L.
Where? See, that this is the problem of doing exercises when.
In the last line, you just.
Yes. What is the problem of the last line? Ah, this is the x, of course. And then?
No, in the beginning, L to the power 2, you know?
L to the power d, yes. L to the power d, absolutely. Okay, so now, if we agree on this, then this is equal to L to the power d over 2 pi to the d omega d. Now I can do the integral, right? So I will get, so let me do all the simplifications later on. Alpha c, then 1, okay, so then I will get x over c to the power d minus 1 minus alpha plus 1 over alpha. So this goes with that. Sorry, and this is not an x, but is an epsilon. Epsilon. All right. And then this is equal to L to the power D over 2 pi to the D omega D 1 over alpha C, and then you will get epsilon over C to the power D minus alpha over alpha. Correct? I think it's correct. Let's see if it's correct. Let's check it. If P is equal to 2 and D is equal to 1, so if alpha is equal to 2 and D is equal to 3, what I get is 3 minus 2 divided by 2, which is 1/2, right? It's exactly what we got last time. If alpha is equal to 2 and D is equal to 2, then you get constant, which is exactly what we got last time. So it seems to be correct. Okay? You agree with this expression? So let me write it then as some constant times epsilon to the power D minus alpha divided by alpha. And now, let me go back to our integral. So now I know what is the density of states, and I have to see whether this thing here has a solution for a finite TC. So how do I do it? Well, I substitute g of epsilon. This is a constant integral d epsilon. Then g of epsilon is is epsilon to the power d minus alpha over alpha, and then I have e to the beta epsilon minus 1. So now, how do I figure out whether I have or I don't? What are the conditions on alpha to have or not to have Bose-Einstein condensation? How do I figure it out? This is a question to you.
If the integral converges.
If the integral converges, then everything will be fine. So now, where can the integral be divergent? For which values of epsilon can the integral be divergent?
For, I don't know, but I think it's for d minus alpha over alpha less than 1.
That's okay, but so where is this integral problematic? For which epsilon? For which values of epsilon you might have a divergent? Well, I mean, is it divergence for large epsilon? For epsilon going to infinity, does it have any problem to be convergent or not convergent for large values of epsilon?
I don't think so.
No, because it's exponentially decaying. So the only problem is for epsilon close to 0, right?
Yes.
So therefore, let me expand the integrand for epsilon going to 0. I will get epsilon to the power d minus alpha over alpha divided by beta epsilon, right? Which is epsilon to the power d minus alpha over alpha minus 1 times beta, right? And now what do we want? We want that d minus alpha over alpha minus 1 is larger than what? Should be larger than what?
And 0.
No. Why should it be? I mean, if you have an integral over dx between 0 and plus well, between 0 and something, some number of x to the power b, well, gamma. Gamma should be larger than what in order for this integral to be convergent?
Then the number, this number.
This integral here is convergent for which values of gamma? Is it convergent for gamma equal to -1?
No.
No. Is it convergent for gamma equal to -1/2? Yes or no?
Is the number sign finite?
Yeah, the number is finite. This is just a number. Let's call it, I don't know, 1. Okay, so when is this integral convergent?
If gamma is greater than 0.
-1.
Oh, no.
Ah, wait, because it
When
it
gamma
depends
is
on the
greater
0.
than what?
Depends on the yeah.
Gamma is greater than what?
It's greater than 1.
No,
Huh?
no,
Yeah.
no. Guys, you cannot, I mean,
Wait.
this is basic analysis. These are things you should know by heart. I mean,
-1 is
Someone said it correctly before. I don't know who said it.
it's Pooja.
Gamma greater than
I
what?
think it's -1.
-1. Gamma should be greater than -1. Okay. So let me check one thing with you. This integral is convergent for gamma greater than -1. This integral here, what is the condition on gamma in order for it to be convergent? This is not equal. This is actually smaller. So what is the condition for the convergence of this integral?
It should be smaller than -1.
Should be smaller than -1. Okay, so guys, this is super important. These two things, I mean, if you're not convinced, just do the integral. It's straightforward to perform these integrations. Compute the integral between a and b dx of x to the power gamma. And now take the limit of a going to 0 or b going to infinity and figure out when is convergent and when it's not. You see, this integral is simple to do. Is 1 over gamma gamma plus 1 x to the power gamma plus 1, right? And then you have to evaluate it between a and b. And then you see that this is 1 over gamma plus 1 b to the power gamma plus 1 minus a to the power gamma plus 1. And now you see that when a goes to 0, so if you send a to 0 and b stays finite, so when is this limit for a going to 0 of a to the power gamma plus 1 finite? Well, for gamma greater than -1, right? For gamma greater than -1, this limit is actually equal to 0. Otherwise, it blows up. And same thing for the limit for b going to plus infinity. So that's how you obtain the two conditions. These are things of elementary analysis that you're supposed to know. Okay? So there is, if you want to be a theoretical physicist, these are basic facts of life. Okay? Anyway,
Yes.
so this should be greater than what? Then d minus alpha over alpha minus 1 should be greater than
-1.
-1. Okay, excellent. Which implies that actually alpha should be, well, if we assume that alpha is positive, otherwise life is complicated, but alpha should be between 0 and b. Okay? And that's it. This is the condition. So you see how it works. It's actually simple. I mean, if we didn't have this, you just compute the density of states, you plug it in the formula, and then you compare. You see this divergence, a divergence for small epsilon is called in physics an infrared divergence. Why? Because infrared light has low energies. And while a divergence for large epsilon is called in physics an ultraviolet divergence. Why? Because ultraviolet light has large energies. Okay, so here you just have to figure out whether you have in this integral an infrared divergence or not. And this is the condition not to have an infrared divergence. All right, so therefore, even the final exam, you would get something like estimate whether you do have or you don't have Bose-Einstein condensation for this system, blah, 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 and how the condensate fraction depends on temperature and so on and so forth. In practice, what you have to do is just be able to calculate this integral, okay, and nothing else, and to estimate its convergence or its divergence. Nothing special. All right, so now, well, let me start with the next topic, which is black body radiation. Well, I'm sure that you're all familiar with the story of black body radiation.
Professor?
Yes.
Wait a bit. Can we go back to the previous one?
Yes.
Just why is it greater, not smaller? I was kind of thinking a bit because when I calculated, like I got like d minus alpha over alpha smaller than 0, I think.
No. So why is it greater than 0?
Yeah. So.
Well, look at what is written here. So the integrand goes like e to the power d minus alpha over alpha minus 1, right?
Yes.
So if this thing is smaller than 0, then it means that the exponent is smaller than -1. But if the exponent is smaller than -1, the integral is not convergent. Here's the following. So let me ask you again.
I mean the one at the infinity.
Not at infinity, at 0 is not convergent. Is this integral here convergent?
Yeah. Yes.
Yes? Okay, let's do it. X to the -3/2, right? Dx, integral between 0 and 1. So how do we do this integral?
Minus half.
Minus
2x minus half.
Wait a second. So it's minus. So this is 1. So this. Why minus half?
Okay. Wait. Plus 1, right?
Anyway. Did you do it?
Yeah, I think it diverged.
It's divergent, right? Because it's a minus 2 x to the power minus 1/2 evaluated between 0 and 1, which is plus infinity, actually minus infinity. Well, it blows up to plus infinity. So you see, that's why it should be positive. Because if it's negative, then it diverges. You don't get confused. If you have a function, a power law like this one, so this integral is convergent for alpha greater than -1. And it's actually the opposite in the ultraviolet. So for large values of x, in this case, you require that alpha is smaller than -1. Okay? That's how it is. Anyway, okay, guys. But it doesn't make much sense to move on to the black body radiation now because we still have 10 minutes and there's nothing I can do about it. But so tomorrow we will be talking about black body radiation, and probably we will do also the Einstein theory of specific heat in solids. And then on Tuesday, we will have our last lecture, and well, we will see what we will do. Perhaps we will do, like today, some exercises, a couple of exercises. Okay?
Okay.
Okay, guys. So I'll see you tomorrow at 11 then. Bye-bye.
Goodbye.
Bye.
Bye-bye.